He's from University of Hawaii, where he kind of has two roles. He's an associate atmospheric scientist at the Water Resource Research Center, but he's also associate professor at the Department of Atmospheric Sciences. So just a little bit of background on the Water Center. The Water Center serves the state of Hawaii as well as other Pacific islands and elsewhere by researching water-related issues distinctive to those areas. So Giuseppe did his PhD in theoretical physics at Imperial in London, and then he moved to Hawaii, where he switched disciplines. And just a quick summary of what his kind of current activities are: focuses on primarily on precipitating convection, which he studies using a combination of large eddy simulation, LES, cloud resolving models, and Lagrangian particle dispersion model. Also using observational data from satellites, stable water isotopes in precipitation. And he kind of applies these tools to research topics such as downdrafts, cold pool dynamics, and the study of severe and extreme weather events and how it relates to climate change. Okay, so we're on YouTube channel, and questions are #CGD seminar on Slido. So I'll try and monitor that, and if you have questions, put them in there, and we'll ask at the end of the talk. So Giuseppe, take it away.
All right, well, thank you very much. Thanks a lot for giving me the opportunity to present some of the research that I've done in the last few years. It's a great pleasure to be here. I really like Colorado, and it's, it's a good break from tropical weather, I guess, once in a while. So the research I wanted to present to you today, it's part of a project that I started when I moved to Hawaii a few years ago. And as was said in the introduction, I come to climate science from theoretical physics. And so I've always tried to make it a point to learn how to do observations, which is something that string theorists don't really know how to do and don't really do. And so during my postdoc, I got interested in stable water isotopes and using those to try and learn something about the climate and the atmosphere. And in particular, I was interested in isotopes in the context of tropical weather. And when I moved to Hawaii, it seemed sort of a natural laboratory in a certain sense for these kinds of studies. And so I started this project, which really consisted in just placing some buckets to collect rainfall. And then the project grew from here, and well, I'll present some results, and I'll tell you a bit about the things that we're planning on doing. This is work that I've done in collaboration with Alison Nugent, who was at NCAR at some point for her postdoc, and Brian Pope, both of whom are now at the University of Hawaii. So we're pretty much far from the ocean here, but I really care about tropical islands, and I would really like to advocate for tropical islands here and why it's important to study tropical islands. To begin with, tropical islands are really biodiversity hotspots. An example is the Coral Triangle, that is this area of the maritime continent that covers only a small portion of the planet, but contains about 80% of all coral species and about 40% of the reef fishes in the world. And tropical islands, as you soon realize when you live there, are really, really vulnerable to any kind of extreme weather event, be it tropical cyclone or heavy rainfall from cold fronts or what have you. And they're also really vulnerable to climate change impacts. Some islands are really suffering from sea level rise and face really dire prospects for the future. And so in Hawaii, for example, since we mentioned water and water security earlier, almost all the fresh water in Hawaii comes from the rainfall. And so really understanding the weather patterns and the climate of tropical islands is really crucial for sustainability of the life and of the ecosystems of the islands. Some of you might not be super familiar with Hawaii, and so I just thought I would put a couple of slides as a refresher. So Hawaii is a very big archipelago with islands that which span multiple latitudes. But the main islands, the major islands, are really 8 islands that start from Hawaii Islands, which is the youngest here, all the way up to Kauai. We have Molokai, Kauai, and Oahu. there are about 1.5 million people living in Hawaii, most of whom are concentrated in Honolulu, which is on one of these smaller and older islands. The latitude of the islands is approximately 21 north. It spans from 19 to 21, roughly. And so these are not really in the deep tropics, which is where I did most of my research, but are well into the subtropical regions. And more about that later. And they are characterized by significant topography. And so we have peaks that go from anywhere from 1,000 meters to 4,000 meters. The Hawaii Island, or Big Island, as is also known, as the highest peaks that go well into the free troposphere. And some of the concerns on the islands is that we have a growing population. More and more people want to move to Hawaii, I guess for obvious reasons. And that did not stop even during the pandemic, didn't stop with wildfires or with anything. And so life is beginning to be really hard to sustain. And this is one of the reasons why I wanted to focus on Hawaii today. In terms of the climate, because we are so far southern from the mid-latitudes, it's a bit different from continental United States climate. And the climate is mostly dominated by the North Pacific High. This is a map of sea level pressure average from 2005 to 2008. So the North Pacific High is situated over here. It migrates throughout the year, but roughly, this is the position. And because of its position, it sends northeasterly trade winds almost constantly to Hawaii. They blow roughly between 65% to 95% of the year. During summer, it's more towards the 95%, and during the winter, it's a bit lower, and there are more sort of mid-latitude systems that come and disturb the climate. But otherwise, it's just trade wind weather, and we'll see the map of the rainfall in a few minutes. But the trade winds essentially are lifted by the mountains. Clouds are formed, and it rains. And so the mountain peaks are really, really wet, but some of the islands are particularly arid. And in terms of the seasons, in terms of the climate, Hawaii really has two seasons. There's a dry season during the summertime, roughly, and that is dominated primarily by trade wind weather. And during the wet season, we tend to have synoptic systems that really dominate the scene. And so we have cold fronts or subtropical storms that are known as konalo's in the context of Hawaii. If we look at the rainfall, this is a map of average annual rainfall over the islands. The windward side of all the islands are characterized by fairly high precipitation rates. And as I said before, this is mainly due to the orographic lifting of the air. But you could also see that the climates change really, really rapidly. And within a span of a few kilometers or a few miles, there can be significant gradients from 10,000 millimeters all the way down to 200 millimeters. And so the leeward side of the islands tend to be much, much drier than the windward sides, or in general, the sort of the mountain sides. Okay, last thing I wanted to say before I discuss the results that we had. I understand that not everyone is familiar with water isotopes, which is the main subject of my talk today. So just as a refresher, water comes, like every element, comes in different forms, and different atoms come with different number of neutrons and slightly different masses. And these different masses give these different isotopes slightly different physical and chemical properties. And so processes such as condensation or evaporation can affect water isotopes differently. So that, for example, heavier isotopes tend to condense preferentially compared to lighter isotopes. And so if we reverse engineer this fact, then maybe we have a chance to use water isotopes as a way to say something about the water that we're observing. Learn something about the parcel's history or the processes that it underwent. And in terms of convection and terminology, isotopic composition is generally given as a ratio with respect to a freshwater standard. And this is the ratio is indicated with an R, and it's typically the concentration of a heavier isotope to the lighter isotope. And the heavier isotopes for water are either because one of the hydrogen atoms of water is heavier, or because one of the oxygen atoms is heavier. So oxygen 18 is one of the types of water isotopes, and the other one has a deuterium atom and another oxygen atom. And otherwise, H2O16 is the most common form of water that we have. Okay, and these are usually these ratios, these abundance ratios, are then compared to freshwater standard, and with a little bit of manipulation, we define abundances. And different parcels have, as I try to indicate here, they can have different abundances of these processes. And we distinguish typically between two kinds of fractionation processes. And fractionation is the process in which isotopes are treated differently, if you will. And there are so-called equilibrium fractionation processes that separate different isotopes in chemical equilibrium, but there are also kinetic fractionation processes that happen during unidirectional processes. An example of this would be condensation or evaporation. In Hawaii, there have been observations of isotopes in the past. Martha Scholl was one of the first ones who did these collections in the 90s. And prior to that, the Global Network for Isotopes in Precipitation, also known as GNIP, deployed a site in Hilo. And this site, I'll show some data and some analysis towards the end of the talk, collected monthly rainfall data from 1962 to 1970, more or less. And so the collections that have been done in Hawaii, they were either done very far in the past, and so the 60s, where there wasn't a lot of additional data that we could compare the records with. So no satellites, and just a little bit of reanalysis that could be used, but there wasn't really a lot of data. And there wasn't a lot of climate data in Hawaii like we have now. Or they were done at a very, very coarse resolution. And so a lot of the studies, such as Martha Scholl's studies, for example, these were done for groundwater purposes. And so the records were collected with a frequency of 3 or 4 months even. And in 3 or 4 months, for groundwater, maybe not much changes, but for the weather, there's a ton of changes, right? And so one of the main issues when we looked at water isotopes in Hawaii was that really we lacked a long-term, high-frequency data set. Okay, and this is what I try to do. And what I'd like to do moving forward in the future is really build on this, expanding the network that we build onto other islands, and also to include other kinds of measurements. Here, I'll mostly talk about rainfall, but we're now also collecting water in the soil and in the groundwater. Hopefully, we'll get funds to also collect in the vapor as well. The network that we built is on Oahu, which is the island where Honolulu is. Honolulu is here on the leeward side where the cursor is. And we try to build a network that created a transect across the island. And the transect, we try to give it a northeast-southwest direction, which is more or less the direction that trade winds follow. And so it's not important that you remember the names, but we started from Kailua, which is the city on the windward side, and we placed a bucket here. Then Maunawili is still on the windward side, but very close to the mountains. Then the first on the leeward side is Lion Arboretum, and this is one of the rainiest places of the island. Then we placed a collector on campus, the campus of University of Hawaii, and particularly on the Hawaii Institute of Geophysics. And then one in Waikiki, which is in a very, very leeward side, although this we discontinued because when COVID happened, it became very hard to go and collect every now and then. So we started in July 2019, and the collection is still ongoing. We try to collect every week, and we're planning on doing daily collections this coming winter with collaboration of a team from Potsdam who develop automatic samplers. For these weekly collections, we're using Palmex rain collectors, and these are nice because they're slightly more sophisticated buckets, but this additional sophistication makes it possible to prevent evaporation, because evaporation would compromise the isotopic ratio of the data set, and they also don't require mineral oil, and so they're a lot easier to operate. And we employed the help of many, many undergraduate students who really made this possible with their tireless efforts. So we're very grateful to them. So here I try to give an idea of the rainfall that we collected, just to have an idea of the different amounts that are collected on different islands. on different sites. And here on the top right, I'm showing a cumulative distribution function of the rain rates that we measured. And the rain rates here are simply the amount of water we collected in a bucket divided by the number of days that we left the bucket out. And here I'm showing a time series. We analyzed the data until August 2021. So we have 2 years of data, and we're now processing the other 2 until August 2023. And essentially, you can see that here the blue shades indicate wet seasons and the right ones indicate dry seasons. One thing that you'll notice is that during the wet seasons, unsurprisingly, there are pretty large spikes, and these are due to synoptic systems that I mentioned before, so subtropical storms or cold fronts passing on the islands, whereas the dry seasons are, as the name suggests, a lot drier, obviously, and these are only very small spikes every now and then. This spike over here in August, end of July 2020, this was Hurricane Douglas, which came really, really close to the islands. And if we look at the rain rates in the different sites, they're fairly similar, except for one outlier, which is Lion Arboretum. And Lion Arboretum, just to remind you, is just directly downwind from the mountains. And as I said earlier, this is one of the rainiest places of the island. And so this is completely, off the charts compared to the other sites. The signs that you see here, these are based on monthly summaries of the National Weather Service. And I tried essentially to categorize the main disturbance that happened the week that we collected. So I distinguished between tropical cyclones, upper level lows, cold fronts, and conalows. And these are obviously mostly concentrated during the wet seasons. And this will be relevant later because I'll divide the samples in samples with disturbances and sample without disturbances, meaning mostly trade wind showers. Okay, so conceptually, when we think about the island, this is the amount of rainfall that the average annual rainfall on the island, and this is sort of the picture of the transect. These are the different sites that I outlined here, and this is an idealized parcel that travels over the island. It is lifted by the topography here, and it condenses, and it rains a lot. And my expectation looking at this was that if we consider one isotope such as delta 18, my expectation would be that the isotopic composition would start from a given value, and then this value would decrease progressively as the parcel travels through the island. And this depletion, I thought it would be due to the rainout. So as I said earlier, heavier isotopes condense preferentially, and so they fall out faster. And so the more the parcel travels, the more it's depleted of heavier isotopes. And so I thought it would go down and down. And then as we move on the leeward side, then here rain evaporation really starts to become important. And rain evaporation, I thought it would have the opposite effect. So it would make the parcels more enriched. Okay, so how does this compare to the results? Well, the picture is shown here. This gives the volume-weighted average of delta 18, so of the isotopic composition. And if you look at the yellow dots, these represents the averages computed over the total period. And I further divide these as between averages during the dry period and averages during the wet season. And as you can see, if we concentrate for a moment on the total period here, the results are actually completely opposite to our expectation. And so rain appears to become more and more enriched as the parcels travel across the island. And this is fairly true. This remains true more or less even during the wet season and during the dry season. We can also look at a breakdown of not at averages, but we could also look at time series of the isotopic compositions. And this is, we've seen before, this is a time series of rain rates for the last 2 years, for the first 2 years of the collection. And these are the isotopic compositions. And one thing I wanted to point out is simply the large variations that we have during the wet season. And so whenever we have disturbances coming over the island, so cold fronts or conalows, we register really, really low values, and values tend to be more uniform during summer and more a little higher during summer than during the wet season. One thing that sticks out is also that one of the sites on the leeward sides, pardon me, this is the one on campus. This tends to have systematically higher abundances compared to the other sites, particularly during the dry season. Okay, and so when we look at these averages, this really sort of defied my expectations in a way, and so we try to understand what was going on here. And one of the things that was missing in the picture that I showed you before with the sort of the cartoon with the parcel going over the islands, one of the things that was missing is that the islands are actually really, really green, and so there's a lot of rain evaporation that happens through surface latent heat fluxes. And these tend to be more enriched compared to the vapor, and so they can contribute to the progressive enrichment of the water parcel as it travels through the island. So this could be one of the factors that we hypothesize could contribute to this enrichment over the islands. Another thing that we think could have also compromised the initial picture was that the systems that we observe rain with different frequencies in different parts of the island. And so when we consider, for example, large synoptic systems, these are driven by large-scale dynamics, and when they come on the over the island, they rain everywhere, more or less, with similar rain rates. But if we think about trade wind showers, these tend to happen primarily next to the mountains, and they stop almost immediately downwind of the mountains, and so there isn't really a lot of how can I say, influence on the other sides. To further check this, we looked at here we're comparing the daily accumulation on campus, which I remind you is further downwind on the leeward side, and we compare it with daily accumulation at Lion Arboretum, which is one of the rainiest spots on the island. And you see that for many days in which we have daily accumulation at Lion of 10, 15, 20 millimeters of rain, on campus we have less than 5 millimeters of rain. And this is the graph here on the right panel shows exactly the same information, but is shown as a cumulative distribution function. And you see that, for example, during the dry season, there's about 70% of the times when it rains at Lion, it's not raining on campus. And because trade wind showers tend to be less depleted than other synoptic systems, the fact that it rains more towards the mountains, this could contribute to diluting the signal that we're observing. So these are two hypotheses. And a third hypothesis is that there could also be equilibration effects that are due to the fact that temperatures over the islands are obviously not equal. And as you go towards the mountains where it's a lot greener, sensible heat fluxes next to the mountains tend to be much, much smaller than latent heat fluxes, and so temperatures tend to be colder. And so equilibration might actually push the vapor and the rain to be slightly more enriched. Another way of separating these data is, instead of using the season, we used the presence of a disturbance. And so here we're showing in purple the isotopic composition during weeks where there was no discernible disturbance over the islands. And so these are primarily driven by trade wind showers, and the green are weighted averages during periods when we had disturbances. And at this moment, we're not distinguishing between different disturbances because we don't really have a lot of data, but we hope to do so in the future. And you see that in the weeks where we don't have any disturbances, so trade wind driven showers, these tend to be a bit closer to the picture that I gave before, where the rain becomes more depleted as it travels across the island. And then here, probably as a combination of the factors that I mentioned earlier, it gets slightly more enriched when it gets to Lion. Weeks with disturbances, on the other hand, are the complete opposite of what I showed earlier, where the sites at Lion is a lot more enriched than all the other sites. And one thing to bear in mind is that we are collecting at a weekly frequency, and because of that, we have a disturbance that happens perhaps one day, but the other days can also be contributed to by other kinds of rainfall, such as trade wind showers. And so some of the dilution that might happen here might be driven by trade wind showers. Another thing we wanted to check was whether we can observe the amount effect. And since we're collecting on a weekly basis, we thought we should be able to observe the amount effect. And the amount effect, if you're not too familiar with it, is the empirical observation that there is an anti-correlation between the rain rate and the isotopic composition of the rainfall. So this is, for example, a picture from one of my earlier papers. And it's showing monthly rainfall collected over the Pacific by the GNIP network that I mentioned in the introduction. And here I separated Western from Eastern, and this bears no consequence for the presentation. But the main point here was that as you go towards higher and higher precipitation rate, the rain becomes more and more depleted. And this is a fairly robust phenomenon that has been observed in the tropics. And it's been observed not necessarily on a single event basis, but when you collect for more than 7 to 10 days, then this tends to be a fairly robust observation. And it's important because it's used to interpret paleo records that are collected precisely along the tropics. There's still some debate over what causes it, but this effect should be observed. So here, these are a lot of plots, and so let me guide you through them. If we look at the top left, the different colors indicate the different sites, and the vertical axes represent the isotopic composition of the rainfall, and the horizontal axis, this represents the rain rate at different sites. However, because different sites rain differently, and I showed before that Lion Arboretum, for example, was receiving a lot more rain, we decided to plot them not in terms of the absolute rain rate, but in terms of the percentile of the rain rate. This made it possible to put all the different samples in the same plot, and to some degree to compare them in a somewhat fair, even fashion. And the top left is the full collection period, and then we separate it in wet season here, top center, dry season, top right. And then bottom left is weeks that had disturbance. Bottom center is weeks that had no disturbance. And here on the bottom right, I'm showing for each one of the sites that we have, we computed, the Spearman correlation coefficient for all the different collection periods. And one takeaway message here is that some sites, such as, for example, the one on campus or the one in Kailua, so the sites that are far from the mountains, and to some degree also the one in Waikiki, the correlation coefficients for all of these is definitely significantly different from zero. And it's pretty, it's pretty decent, it's pretty significant. You could also see it also from just, eyeballing through these plots. But as you go closer to the mountains, then the story becomes slightly more complicated. And for example, at Lion Arboretum, if we look at the Spearman coefficient, for example, for the dry season, this is roughly slightly positive, and in any way, it's not significantly different from zero. Same for the non-disturbance weeks. And Mauna Widi, which was windward, but still very close to the mountains, again, during the dry season, we don't really observe any kind of anti-correlation. So we do observe the amount effect on some part of the island, but we don't really observe it for all of the island. And again, because some of the paleo records that are collected in Hawaii are being interpreted using the amount effect, I think this is an interesting finding, because it suggests that some caution should be taken when we interpret these records. Another thing that we measured was the deuterium excess, and this is a second order parameter that is often used to study the source region of the water parcels. And here I'm showing the time series again for deuterium excess for all the different sites. And these show pretty distinct seasonal cycles with higher values during the winter and lower values during summer. And the site on campus, the one here in the red, is also systematically lower than the deuterium excess of all the other values. of all the other sites. And these lower values we interpret as being due to essentially rain evaporation that occurs mostly in the leeward side of the island. And as for the seasonal cycle, this to some degree we attribute to the different source region. And so we did some trajectory analysis using the high split model. And here I'm showing on the left panel some trajectories that we backtracked for 1 week during the wet season. And on the right, it's the same, but for 1 week during the dry season. And these are only 1 week, but these are fairly representative of the conditions that we have. And the colors represent the altitude of the trajectories. And unsurprisingly, given the climatology of Hawaii, during the wet season, we have a lot of air parcels that are coming from really far, sort of from Asia and from high altitudes, whereas in the dry season, they tend to be more locally sourced. However, one interesting thing is that if you actually look at these parcels and how these parcels are traveling, you notice that these tend to be, most of these parcels spend the last 2 or 3 days before coming to Hawaii, mostly in the boundary layer. And because of this, it's fair to assume that these parcels really receive a lot of influence from the boundary layer. And so it's okay, I think, to use deuterium excess to infer something about the source region, but we also be mindful of the fact that if a parcel spends 2 days in the boundary layer, the conditions with which the parcel arrives at the islands are probably representative also of what happened in the boundary layer. And so we combine the high split trajectories with ERA5 data, and these show that the x-axis shows the height of the parcels, the x-axis shows the time prior to their arrival. So 0 means that the parcels arrive on Oahu. This is 1 day earlier, 3 days earlier, 2, 3, 4, 5 days earlier, and so on. And here I'm comparing the difference between the relative humidity from the dry season and the wet season. And I'm also comparing here the different values of sea surface temperatures that the parcels experience. And one thing that we see here is that, unsurprisingly, the relative humidity that parcels experience in the boundary layer is a lot larger during the dry season, with values up to 10% higher in the dry season, and also sea surface temperatures are much, much higher during the dry season than during the wet season. So this is completely consistent with these seasonal cycles with larger deuterium excess values during the wet season than during the dry season. But the point I wanted to make here is that this is probably a combination of different source regions, but also different conditions that the parcels experience in the boundary layer. I wanted to conclude talking about interannual variability. And you might ask, how can we talk about interannual variability if we have 2 years of data? And in fact, we can't. And so that's why for this one, we used the GNIB data that I mentioned earlier. As a reminder, GNIB collected from 1962 to 1970. It was not on Oahu, it was on Hilo, but Hilo is on a big island, it's fairly close. And it collected monthly instead of weekly. Nevertheless, for some of the things that we want to look at, I think this might still be a fairly good data set to look at. And what I'm showing here are the values of the precip abundances during the wet season on the left and the dry season on the right. And here I'm plotting on the x-axis the delta 18, on the y-axis the delta deuterium, and the colors represent the years. So the blue are further back in the past. So let's say 1962 is the bluest, and 1970 is the most yellow, if you will. And one interesting thing is that for the wet season, there is fairly significant variation. And some years, so 1962 and 1963, have really, really enriched values during the wet season. And other years, such as 1968 and 1969, they're really, really depleted compared to these values. This is not necessarily surprising because we do know that the climate in Hawaii is very sensitive to the conditions of the Pacific. And so obviously the biggest thing that happens in the Pacific arguably is El Nino. And so during El Nino years, the jet shifts position. And so this influences the kind of disturbances and also the number of disturbances that affect the islands. And so during the wet season, it makes sense that there is such a large variation. During the dry season, on the other hand, the variation is a lot more nuanced in a sense, and point tends to be more concentrated towards a running average. And another way to link the variability that we were observing with sort of the larger scale is we did a linear regression of the delta 18 values that were observed by GNIP, and we regressed these with monthly averages of sea surface temperatures over the entire Pacific. And and as you can see, there are significant anti-correlations in the area next to Hawaii and significantly positive correlations on the western side of the Pacific. And so this suggests that when the Central Pacific gets warm, then the water isotopes become more depleted. And when the Western Pacific becomes warmer, then water isotopes become more enriched. Of course, this only includes 8 years of data from GNIP, and so this is also too short, let's say, to draw some final conclusion. But one interesting thing here is that I think that there is some potential to link this, to link these data for studying the variability in the Pacific, and because there seems to be this this map of correlation seem to distinguish between the Eastern and the Central Pacific, there might be a way to use this also to differentiate between the Central Pacific El Niños and the Eastern Pacific El Niños. This is obviously just speculation and well-wishing because, let me stress it again, we don't have enough data, but we hope that with time and patience, we'll be able to collect enough data to say something more about the interannual variability that we observe. Okay, so just a conclusion. I presented today some new observational network and some new data set of water isotopes in Hawaii. We collected rainfall data at a weekly frequency since 2019, so we have about 4 years of data, but we're hoping to expand this to, first of all, daily frequency. We hope to expand this to other Hawaiian islands, and we're hoping to really include other variables such as soil moisture, water vapor, stream water, or fluxes from the ocean. Some of the take-home messages that I thought was interesting were that, contrary to what was my intuition coming into this, the rainiest sites had the highest isotopic ratios and not the lowest ones. We did not observe the amount effect at all sites, and I think, as I said earlier, this is significant because the amount effect is often used as a standard lens to interpret paleo records, and this, along with other records that were taken on other islands, suggests that the story can be a little bit more complicated than that. The deuterium that we observed had a marked seasonal cycle, and this is really due to a combination of different sources of air, but also of the different properties that the air encounters. And some of the data that we observed in the past through GNIP showed substantial interseasonal variability, although much more data and a much longer collection is needed. So maybe invite me again in 30 years and I can tell you more about the interannual variability. Anyway, well, thank you so much for your attention and happy to answer any question.
Thank you, Giuseppe. That was super interesting. Any questions in the audience? Yep.
I wanted to go back to the moisture recycling argument that you mentioned. Is there like a cause and causal direction to that? I was wondering if it's more enriched. The evaporation at these high rain sites are enriched just because the rain that's coming down on it is enriched. Also, I was wondering if like the whole evaporation aspect, correct me if I'm wrong, aren't the lighter isotopes preferentially evaporating, or in that case, like does that
That's right.
work against?
Yeah, so unfortunately, because we don't have, thank you for the question, first of all. Because we don't have soil moisture data, we're not able to really draw some causal arrow here. And it was mostly us trying to provide some hypotheses for why we observed that. So take it as a conjecture that is what could happen. And you're correct that the evaporation would then favor lighter isotopes to evaporate. And that was the argument that, the core of the argument that I think I was trying to make. So the lighter isotopes would evaporate, and potentially they'll be entrained by incoming air parcels, and this would enrich the air parcel. So imagine the air parcel is losing heavy water isotopes, but then some of these would then feed back into the parcels, and so potentially it would re-enrich the water parcels in heavier isotopes.
Okay, I don't see anything on Slido, so please post if you want a question asked. Anyone? Isla?
Thanks. So you briefly mentioned paleo records, and then you showed these links with SSTs. I'm just wondering, is there scope for reconstructing SSTs in that region?
Yeah, I think I haven't really dealt with paleo records before, but I think, yeah, that would be one of my interests in seeing if we can, at least in the local region. I don't know if these correlations would be significant far away from Hawaii, but at least in the local region. I guess one of the questions when we look at SSTs in the Pacific is, one of the questions is how ENSOs, how the different flavors of ENSO have changed, for example, through the years. And so do we observe more Central Pacific ENSOs or more Eastern Pacific ENSOs? And so one of the things I thought was maybe we could use some of the paleo records collected in Hawaii to potentially try and say something about ENSO, yeah.
Anyone else? Question? I'll ask one if no one else does. Oh, was that a hand? Yeah, sure. Jesse's got one.
Hi, Giuseppe. Good talk. I was curious, could you describe just a little more about the meteorology, maybe after the trade wind events? Like, I assume the wind comes in, gets uplifted by the mountains. I mean, does then like deep convection occur? And if so, then does on the leeward side, is that kind of just amble basically coming from that and raining down, or is it like spill over to a new cloud system? Yeah, more description would be great. Thanks.
Yeah, no, thank you. No, actually, for better or worse, deep convection is just, it doesn't happen in Hawaii because the inversion is really, really strong for most of the year. And so the cap of the trade wind inversion is about 2,200 meters, 2,500 meters. And so clouds really just grow a little bit, but they remain shallow cumulus clouds, and there's no anvil to speak of. And they go up the mountain, they rain, but then after they've passed the arboretum and sort of the greenest areas, they just dissipate and they vanish completely. Exception to this is during the wet season, when sometimes we have low pressure systems that are coming much closer to the islands, and these sometimes lift off the cap, and these make deep convection happen. But I've been there 5 years, and maybe I heard thunder 4 times, maybe. So yeah.
So I have a question. In the largest scheme of things, in terms of sea surface temperature, water mass formation, regions, is there an understanding of how isotopic, like depletion, isotopic content varies with reference to that, and even maybe surface wind speed? I just don't know. If you plotted a map of global isotopic concentration, would there be much variation in the ocean, or would there be some regime-specific differences?
I'm not an expert on that.
No, it's fine.
My honest answer is I don't know. I would imagine that just because the properties of the water change, such as temperature, for example, I would imagine that there would be some variations with latitude and also longitude.
Yeah, I'm just wondering, like the further upstream origin of the the wintertime systems versus the and what is happening between there in terms of the surface interactions.
Yeah, so there is some indication that I think the relative humidity near the surface and the sea surface temperature also control not only the isotopic composition, but also the proportions of the composition, so the deuterium excess that I mentioned earlier. And so I would imagine, I don't know that I could draw a map right now on top of my hand, but I would imagine significant geographical variations, yeah.
All right, nothing on Slido. Anyone else in the room? Okay, well, let's thank Giuseppe one more time.
Thank you very much.